Again, good afternoon, everyone. Good morning, those who are in the central time zone or west of us. Welcome to today's virtual consulting office session organized by iGuide. iGuide is the Institute for Geospatial Understanding through an integrative discovery environment. And we conduct this VCO series on an almost regular basis in a weekly fashion. Today's presentation is from Carson, and you can see kind of the list of our other presentations going on from iGuide in the next couple of weeks as well. So the next 3 weeks we have them already scheduled. So if any of those topics are of interest to you, you can sign up and join us. The link, we have a link there on the QR code on the left-hand side of my slide, which shows kind of how to get additional information about iGuide, the iGuide mailing list, so you can join them and you can get up-to-date information about the things happening in iGuide. But again, today's session is a virtual consulting office session. My name is Anand Padmanabhan, and I'm a research associate professor at the Department of Geography and GI Science at the University of Illinois Urbana-Champaign, and I play the role of a managing director for iGuide. Today's presentation would be from Carson, and Carson will be talking to us about open science and reproducible workflow with urban taxonomy and OSPD. So Carson has worked with OGC in order to take this work to the next level. So, and he is an expert in remote sensing, geospatial AI, and those kinds of fields. And he's taking this as a company to the next level, to as products to the consumer. So, taking research out to the field, as we like to say it. So it's really important work, and we will be happy to hear from Carson about what his work has shown us and what are the next steps and how he would try to engage with us. So with that, without much further ado, I will pass on the stage to Carson.
Thank you, Anand, and thanks everyone for coming. I'll just start sharing my screen for the presentation. And can you please tell me if you see my slides?
Yes, I can see your
Perfect.
slide. Yep. Yeah.
Okay, so today I want to talk a little bit about open and reproducible science and my experience in it. I've worked on it from several angles. So first I started off as a PhD student and then as a postdoc, where I worked on a big project called Urban Taxonomy. And I will briefly introduce the project, which is interesting in itself. But why it's relevant and why I want to talk about it today is that it is also a project where one of the things we tried to do was make it as reproducible and as open as possible. We tried to contribute all of the relevant functions that came as outputs from this project to upstream and downstream packages. We have a lot of the final intermediate data products available. And in general, we try to make this project a community effort as much as possible. I will talk about some of the challenges that we faced along the way. Then I'm going to talk a little bit about some initiatives that currently I am involved in or that I know about that are making fair and open science easier and addressing the challenges that I'm going to introduce. And then I'm going to talk a little bit about specifically one about the OGC, words led by the OGC, the OSPD, Open Science Demonstrator, which aims to make a lot of scientific workflows open and reproducible, our involvement in it, and how it helps to tackle some of the challenges. Right. So, what is urban taxonomy? In general, it's an academic project, right? It's a ongoing thing. It's been happening here in England and in Czechia for, I think, 5 or 6 years. I got involved in at the end of it, but it's a big project with that's primarily led by Dr. Martin Fleischmann from currently at Charles University. And it's the main idea behind it is to provide a quantitative classification of build-up fabric. So think about the configuration of buildings and streets, their compositions, and the different patterns that they take. And the whole idea is to take the whole of Europe and classify the entire urban fabric, similarly to how you would classify a tree of life. And you can see some of the results here at the very right. This is something akin to the tree of life, where instead of having mammals, fish, and so on, you have the different types of built environments. So here at the bottom right, you have the medieval. At the top in the center, you have sort of more modernist building patterns, and then at the top left, you have more industrial building patterns, and so on. In general, how the whole approach works is we start and we analyze the individual polygon of every building in Europe, and then the individual street that building lies on or is connected to. We generate something like 50 different features for it. Then that we call morphometrics. We link them back to the buildings. Then we use a clustering algorithm that we call SA3 to create what we call morphotopes, which is the smallest unit that exhibits consistent morphological patterns. So you can think about it as like a neighborhood that has like a consistent plan. And then we create a hierarchy of those that you can cut at different levels to achieve a classification at different scales. So you can see at the top right, at the top, everything falls within a single cluster. As you cut the clusters, you get more and more granular distinctions. So I can actually show a little bit about the website, because it's nice to see the interactive map of the whole thing and see it in action. So you can see here the city of Prague, and you can see here the hierarchy that goes up to several levels of detail. And as you click through it, you get different patterns in different cities, and then there are different explanations of what these mean, how they can be interpreted, and what they can be used for, and so on. In general, this work has resulted in a research paper, a data set, and we've released the code. One thing that we are particularly proud of, the entire team, is that the entire SA3, the entire functionality that was required for this has been contributed to open source science packages, SPOpt, MonPy, LibPy, Cell-Shapely, GeoPandas, and so on. So these are open source libraries that are widely used by both scientists and industry and so on. And one of the contributions that we're really excited about is that we managed to push a lot of that work upstream and downstream, so that we don't just get the academic. So we don't just have an academic impact, but we also have some impact in the software community, give back to the people who we work with, and so on. In the process of doing that, and in the process of having the paper, the code, and the data, and then having an interactive website, we came across many different challenges. I've separated them out in data challenges, code challenges, and then packaging challenges. Some of them I'm sure you're familiar with, because they are problems for anyone who actually has had to work on a project like this one. For example, we've had a lot of challenges with access to the raw data. So because we were covering the whole of Europe, we ended up covering something like 100 and something million, building a processing chain that covers several 100 million buildings and polygons. And every administrative region had its own API and format and so on and so forth. A lot of people are still using things that are transferring, let's say, GIS data in XML formats and through XML files and so on. So that was painful to process and to put together. Another one of the challenges that we had was, once we had the access to the raw data, it was separating out the raw and the process data, which is something that I guess everyone that has to deal with an analytics project has to deal with. And then it was data versioning and storage. Even though all of the polygons came from cadastre data, a lot of our street data came from Overture. But in the meantime, as the project was going on, Overture changed the schemas for the street data, then changed their host requirements. At one point, we lost access to all of the hosting data because they only keep old data up to, I think, 6 or 3 months. And that was at that time when we were writing the paper. I don't know what the what the current conditions are. In terms of software, what we came across was a lot of problems with versioning and updates. Because we wanted to contribute to the libraries and because this was an ongoing process, we had to keep very different versions of the libraries and of our software stack online and operational at the same time. We had some we could not even install. We had to download and build locally to create the stack that we needed to. We couldn't even use, we could use Docker containers and so on, but even those could not be made reproducible because we needed to tinker manually with the different libraries to make them work together. Because, for example, as we pushed one piece of functionality to an upstream library, it would not get released for a few months, but we needed this functionality to work with another local version of the library. So this was a challenge that we had. Another one was basically the reproducibility, which is something that I think everyone here has to deal with. We needed to package the work somehow so that it could be easily executed by multiple people on multiple machines. We generally managed to find a good balance for that using Python tools like Pixie and so on, but also that was one of the challenges. And then another thing was managing the upstream and downstream contributions. Specifically, that was which piece of software goes where, when, and how. Because we wanted to contribute to upstream software libraries, we needed to actually keep track of many different release cycles. We needed to keep track of what is actually possible, what can go where, and what we can archive for later processing. Currently, all of the code for the project is available. A lot of the functionality is contributed upstream. However, there are still some things that of lower priority that can still go into one of the mainstream libraries that lots of people use. And then the big challenge is, okay, we have a website, we have a paper, we have code, and we have data. And the question was, how do we package all of this together? Currently, we're just using the website as the main reference point. The paper links a little to the website, and the code links to both the paper and the website and the data. The data only links to the data because it's hosted on Zenodo. So it's a challenge of like, how do we present this to everyone? We currently, I think, mostly use the website and the paper since it contains links to everything. But in general, I think the experience with this research project is nicely encapsulate a lot of the challenges that we have when we are trying to work with open science and make it reproducible, but also go one step further and contribute generalizable solutions back to the community, into the libraries, into libraries, modules, and packages that people can reuse, and not just reproduce our own work and our own papers. So as I've left sort of this project, as I finished it off, I've been involved a little bit in these FAIR and open science standards and initiatives, and I've come across certain things that can actually start helping us to better manage and to help us create more open and fair science. These are things like standards, such as the FAIR standards, which we'll talk about in a little bit. It's initiatives in communities such as EarthCODE or the Turing Way, and then it's specific journals that are dedicated for data and code and experiments, which are reproducible and peer-reviewed. And then there are initiatives like the OGC, the test beds for standards, and they bring together people from academia and industry to work together on standards to create more reproducible workflows for scientific code. So the fair and reproducible standards were first defined by a version of them were first defined by Wilkinson in their 2016 paper, and they provide a structured approach to managing data so that it's more reproducible. It can be discovered, accessed, and used by multiple people and teams. They specify certain types of criteria that need to be fulfilled in order for the data to be considered fair by their standards. And there are different tools and validation schemes that people try to implement to verify that whatever they're producing is fair and open and so on. One initiative that tries to implement this specifically is the EarthCODE initiative from ESA, which stands for Earth Science Collaborative Open Development Environment, which tries to bring together platforms, long-term persistence, metadata cataloging in order to, and community work in order to accelerate scientific discovery through digital innovation. The idea is that it's a one-stop shop for everything required to create open science. It provides you with compute, it provides you with storage, it provides you with standards, and it helps you throughout the dissemination and publication process. Another thing that helps with this work is the OGC OSPD, which specifically tackles a part of the Earth and is also involved with EarthCODE, and that is, and specifically focuses on scientific workflows. And what it aims to do is develop and validate a framework to describe, share, and reuse scientific workflows. And this is what we were involved in. And this is sort of how what we brought to the table was the experience with the problems that we had actually doing research, our experience with EarthCODE and helping people manage the entire open science lifecycle, and to try and use and automate the extraction of workflow logic to sort of achieve fairer scientific principles. So the idea was to create a series of experiments and to create a series of works so that we can actually help the scientists avoid the cumbersome work of reworking their code or putting it in different formats or different standards and so on, and let the AI agents and machines take over that. In the context of having strong validation tools, right? The idea wasn't that we just take an agent and we let it run wild, but that we actually provide strong validation tools to know that what actually has been outputted by the LLM process is actually verifiably correct and verifiably similar to some sort of standard and to what the scientists expect. So how did we do that? Well, first of all, we started off with 3 experiments at 3 different levels. We started off by automating the metadata generation, and this provided an automated description of scientific workflows. Then we started automating CWL generation. So in the first step, we found out that it's actually easy to generate metadata. However, generating executable workflows is actually much harder. Therefore, we focused on another validation and execution engine. We added execution to one of the requirements. And then in the third one, we took what didn't work out in the second experiment and tried to improve on it through direct code graph analysis. So in detail, what we did in the first experiment was basically we selected a standard from the OGC building blocks to act as a validator. There is an agent that generates metadata, and then it tries to validate the loops, and it tries to validate whatever metadata is generated so that it can we can actually make sure that all of the extractions are working fine. How the entire workflow looks in detail is we feed into an LLM all of the source code, all of the data, all of the documentations, and so on. And then we use the metadata profile building block EarthCODE workflows as a validator. So this creates a metadata validator that gives us a rich description of a piece of scientific code that a scientist has run. It covers things like temporal extent, spatial extent, what input data, what output data uses, and so on. And we then try to, once the LLM extracts all of this information from the documentation, papers, repository, and data, we try to validate it against these OGC building blocks. Whatever errors there are, we feed them back, and we try to let the LLM run until it produces some sort of valid result. Basically, what it ends up doing is take into account this work, and it produces geometries, and it produces a JSON file that has all of the information on the name of the workflow, the type of workflow, the access to the workflow, some description of the workflow, whether or not it runs in a container, what kind of language it uses, so on and so forth. However, what we found out in the first example is that the results show that getting syntactically perfect JSON is possible. Getting pretty much any type of metadata is very much reasonable and within the limits of the current LLMs and the current LLMs capabilities. So the issue was that creating executable workflows that actually reproduce an experiment is much more difficult. We would get very nice and very accurate metadata and descriptions of what these functions and what these GitHub repositories do and how these papers are made, but we had no actual way of verifying whether or not that's true. So the takeaway from this experiment was that we don't just need a validation in the loop for the agents, we need an execution environment. So we decided to use CWL, which is a common workflow language specification by the OGC, both as a validation tool and as an execution engine. The workflow is very similar to what we saw last time, which was that an agent generates metadata, then an agent takes in information about the paper, about the code, and about the data. It generates, in this case, a CWL code execution graph. This code execution graph gets validated by the CWL validator, and only after it's validated, then it gets executed. Any sort of errors are fed back into the loop until a valid and executable CWL is generated. This is an example of a CWL file. For people who haven't seen it, it basically is a specification that describes how different Python functions are called, with what type of outputs and in what order, and different limitations on the inputs and outputs. Also specifies paths. What we found as results is that it's actually very much possible to generate CWLs from a repository, a paper, and a data set, provided that there is an execution environment specified. Unless there was an execution environment specified, we had sort of a chicken and egg situation where we could not 100% trust the errors that a LLM found, since sometimes the errors would come from a misspecification of the execution environment. Sometimes it would come from a misspecification of the CWL graph for the code execution. Another thing that we found from the results is that there is some sort of notion of a reasonable input data and output data sample. This is related to the LLM work times and to the LLM, the way that currently companies charge you for the execution of the engine. So basically, you could let an agent run for hours and hours, and you needed some way to stop it if things got out of hand. The trouble is that once you see a workflow, you basically have no indication of for how long the scientist ran the code, unless it's explicitly specified somewhere in the paper, and that's technically not the case most of the time. And also another limitation for the CWL is that the workflow itself is not too complex. And by that, I mean either that the workflow has well-defined components that can follow sort of a command line structure, or that the workflow has some sort of breakdown of logical steps. Using the third experiment, we tried to somehow address all of the issues that came up in the second one. That is, we tried to use deterministic function calls and analyze the actual code structure and the graph code calling itself so that we can technically see what type of inputs or what type of specifications are missing from the metadata and from the paper. So we basically flipped the paper or the problem on its head. If in the first case we were reading inputs, generating some outputs and then validating them against the validator and expected results, in this case we were using the LLMs to generate some outputs, and then we were taking them as ground truth and trying to see what is missing from the original specifications for the data, for the code, or within the paper. So, for example, we would try and get a workflow, GitHub repository, a paper. We would try to create this graph that actually specifies how the code flow works itself. This could be done by running the code. It could be done by also static analysis, and so on. In which case, if you decide to run the code, you would also need examples of input and output. And what this sort of process surfaces is things that are underspecified in the initial work, such as AWS keys that are assumed to be available, or different types of data sets that scientists have not exactly specified that you need neither in the paper nor in the data that they've shared, but they are used in the code. When using this approach, you can handle more complex workflows and you can follow up on some errors. However, this requires a lot more resources, both to validate the inputs, to validate the outputs of the model, to validate that there are no hallucinations. However, if the first two approaches fail, this was a nice fallback that we could use to sort of narrow down what are the next questions that we are supposed to ask. Another drawback of this method was that this is non-deterministic. So basically, depending on what agent you used or when, or we don't know exactly how, different results came up, and we could not consistently produce the same thing. Broadly, if there was a file missing that we couldn't find among the data, among the input data, or there was some sort of secret key specification that was in the code but not described anywhere else, the models tend to surface it, but when they surfaced it and after what prompting, that varied a lot depending on model by model and depending on workflows and whether or not you feed different parts of it, so on and so forth. And basically, what are the conclusions from our OSPD work? Generally, AI tools can help you, and they can help you structure your code to be more reproducible, and they can analyze and break it down into chunks, provided, in general, that there is an execution environment, some sort of notion of running your data, there is reasonable input and output data, and that validation and execution is not too costly. So if your workflow is covered by all of these cases, and then you want to contribute to, and then you are interested in fair and open science, you can start using LLMs, and you can start using a lot of the work that we've done in the OGC OSPD to address some of the challenges that I talked about during the introduction of the Urban Science project. So you can handle the code execution, you can handle the idea of like which code blocks should go into what libraries, whether or not they are sufficiently generalizable, and so on. But overall, there is a lot of human involvement still, and there is a lot of manual work that is required. Nevertheless, these are good starting points for anyone who wants to create more open and reproducible science, at least in my opinion. But again, provided that you actually need a notion of reasonable input, reasonable output, good execution environment, and so on. These are sort of the requirements that you have to do. In general, you can't rely on AIs and so on to help you out. And yeah, thank you very much. And this was my talk. I'm happy to take any questions about either the urban taxonomy, or the OSPD experience.
Questions? I see there is a question in the chat from Francis. Yeah, first of all, yeah. Thank you. Thank you for the presentation. That was nice. Carson, there is a question in the chat. Yeah. Yeah, go ahead. I think Carson, we could hear you till this point. Fine.
Yeah.
So there is a question in the chat from Francis, if you can take that.
Yeah, so no, that's a really good question. And that's why we had this idea. We went to the second way of actually generating executable CWLs, Francis, because there are basically infinitely many things that can pass a validation, and it doesn't guarantee anything. And that brought the problem of, it's basically like writing a test for your LLM, not a unit test, but an integration test for your entire workflow. Then you can sort of guide it. And because CWL is it's a simple enough format. It's just basically calling a specific Python entry point. That solves some of the issues. But again, if your workflow is too complicated, or there is any sort of missing data or unstated assumptions, then it starts hallucinating and spinning, or starts spinning its wheels. So yeah, it's the only thing that we found out that can guarantee it is more input and output examples. So running so running it in a validation loop until the generated CWL works, and it converges depending on the complexity of the workflows. I can share the OSPD workflows that we had, but for example, on the Urban Taxonomy, that was not part of the demonstrator, but I've tried the loop on the Urban Taxonomy. The problem with it is that the code is structured, if you look through the GitHub repository and Jupyter notebooks that call a Python module, if it's structured in that way, and the Python module itself has tests. Basically, I had to take specific functions from the Python module, and the only thing the LLM had to figure out was which Python functions to call with what output and how to chain together the calls, which was chained in the notebook anyway. So in that case, it worked. If there is no such context anywhere, or it has to extract functions from the notebooks and rewrite them, then it didn't work. In our case, it converged fairly quickly because it only needed to do sort of translation rather than anything creative. How did you determine completeness and comparability of completeness between each of the classified classes of morphotopes? So in the paper, this is going back to the urban taxonomy, Sreya. So in the paper, what we do is we pick a level at the taxonomy. We don't analyze the different morphotopes at um, at the morphotop level, but we analyze the hierarchy going from the top and cutting it, I think, at 4 different levels. And we compare it with other morphological data sets, such as the Copernicus Urban Atlas, the data sets that come from ESA on land use, and then the local climate zones, which give a breakdown of different urban areas based on the types of um, urban structures that are there, defined by some models from satellite imagery. So we validate them at a higher level, and we just sort of do confusion matrices. But yeah, we thanks. I'll check it out.
I have a question for Francis. Francis, you mentioned the Jupyter repo to CWL. Is this something new? Is this something that Gerald Fenoy was working on and using? Are you familiar with that work?
I don't think Gerald used it unless he did without mentioning it, but it's not something very new. It's already a few years ago. I've used it in the previous iteration of OSPD, and it relies on another project that I think is just Docker to CityWheel or something like that. So it basically interprets the Jupyter part and then ends off the packaging of the repo into a Docker container and then connects the two ends together. So you get the equivalent of what would be running in the Jupyter notebook into a Docker container. But it still assumes that your dependencies are it's able to infer most of the dependencies and install everything correctly. So some of the issues that was mentioned at the start of the presentation, if you need custom behaviors or packages, you might need to tweak it a bit more manually still.
Thank you. Very interesting.
And something that I think another thing, a lot of the OSPD on this persistent demonstrator, a lot of the Jupyter workflows, they required some sort of interaction in the notebook, which I would think this would also be a problem. So like if the execution is sequential, it could work deterministically. If it requires some sort of tinkering, but it's a problem for the other method as well.
Yeah, if you're waiting for user inputs, you need some kind of workaround to insert that input somehow. Yeah.
And question from you on the iGuide side. So you guys also do a fairly similar work. Like I was wondering, how do you handle that? Like if you have a workflow that has an interactive requirement, like in between, like how do iGuide handle this?
Yeah, I think that is definitely an issue. most of the things we are doing is through the Jupyter notebook environment. We currently have the smart search kind of capability, which allows you to interact with an LLM to to find out things about what's on the platform in terms of the data sets and find connected resources. You can look at that as well. But yeah, that specifically, if you're looking at that problem, it's it's also a challenge. Generally, people are using the Jupyter environment and maybe going somewhere and coming back with some of the input. So that is that disconnect.
Thank you. Very interesting.
But I think the reason I mentioned the platform was, I think Carson at one point mentioned that data, we have these kinds of various elements of codes, data. This they were linked, but then the data is not linked to the code. So I wanted to provide a mechanism where we don't need to host all the data. So we can host the data. We have that kind of capabilities as well. But for data set that is hosted somewhere, we could just have this as a linked element within the platform along with other linked elements. So you create this knowledge network. And the idea would be, if you have code elements, especially Jupyter notebooks, that could be run. We have the execution environment for you to run the Jupyter notebook within the platform. So that's kind of maybe that is a little bit of complementary things in terms of what Carson was suggesting.
And
Mhm.
just on that topic, what do you use to manage the environments for the Jupyter notebooks? I mean, is that
Oh, yeah. We use something, I don't know if you know this. There is a software package coming out of CERN called CVMFS, which basically provides. You can think about it as a NFS, but for a wide area file system, a wide area network, and it does its replications and all those kinds of things independently. So we use that to host various kernels, as well as Conda environments associated with the kernel, as well as we have Docker containers. So between all these three things together, it's done in the backend.
no? I haven't heard of it. I'll check it out. Definitely.
Yeah, that's it was mainly used in physics, kind of where they have like a lot of read-only kind of software. So this is kind of similar in that environment. We have this read-only container, or container, as well as the kernels. So those get mounted, and the advantage of it is now, like, you can run it on the platform on the Jupyter environment, but when you go to the HPC environment, you could have the same kernels available because they could be just mounted. So that helps with kind of scaling and moving across platforms. Yeah, so I guess, Carson, if you have some bandwidth, you could look at the platform and see, like, how it could potentially be leveraged for the work you were already doing.
Yeah, definitely. It's
Yeah. Okay. Any further questions from people on the call? If not, let's thank Carson again for this wonderful VCO session. Thank you so much. And we hope to hear back from you again. And thank you, Sina, for helping lead the OSPD and OGC effort there.
thank you all for coming, and thanks for the good questions.
Yeah. And we'll see you all next week on another VCO.